Okay, welcome everybody to this session looking at the enabling technology programs in relation to wave and tidal that have been going on around the UK. A couple of words first I need to say as a chair for this meeting. Sorry, my name is Neil Ferguson, Scottish Enterprise. There's no particular problems or particular trials that we're aware of, but if any emergency situation does arise during the proceedings today, an announcement will come across the tannoy system telling you that there's an urgent situation and asking you to leave the building in an orderly manner, it says here, to the nearest exit available as directed by the SECC staff. So just to be aware of that. And obviously, if you can put your phones on silent, please, that'd be much appreciated. So the idea of this particular session of the conference, and this is part one of a two-parter, the second part's tomorrow, is to really tell you about the results of four areas of activity that have been undergoing since 2012 in the UK, looking at the development of so-called enabling technologies, so not associated with devices per se, but more to do with the technologies that will support the deployment, for example, of arrays or other systems for the installation of wave and tidal devices. First out the blocks was the Marine Energy Supporting Array Technologies, or MESAT, which was co-funded by Scottish Enterprise and Innovate UK and run by Innovate UK, 2012. We then had the Marine Renewables Commercialisation Fund, which happened a couple of years after that. That was really managed and driven by Carbon Trust with funding from Scottish Government. We've had the Tidal Array Cabling Solution Development Project run by SE, and that will be first up in terms of a presentation today. And obviously work in various guises by the Offshore Renewable Energy Catapult. So our five speakers are going to be covering particular projects across these four programs. As I say, there's a part two tomorrow, and it'll not be like a two-film, it'll be even better than today. So please, if you want to come along to that, that would be great. Yeah, hope you sit back and enjoy some of the results from what have been really intriguing and very important projects for the industry as a whole. So I'll sit down now and pass over to our first speaker. Okay. And our first speaker is Daniel Wise, who's the head of offshore technology for Aquatera. And Dan's going to tell you about a particular project in relation to this SE tidal array cabling project. Dan's been involved in the whole marine operations area for a while now, and extensive experience across a range of different marine projects, spanning commercial diving, renewable energy, and the dark side of the oil industry as well. So Dan's in a really good position to give you full details about the particular project he was managing with SE funding, and which was quite a challenging one, fair to say, Dan, and but great results at the end of it. So over to you.
Good afternoon, everybody. So as Neil says, Daniel Wise, work up in Orkney for Aquatera. And I project managed this £2.4 million Scottish Enterprise funded project. The project was split over two main phases, the first being a desk-based assessment where 6 companies were invited to take part. And then following that, 2 companies were taken forward to demonstrate in the sea the results of that desk-based assessment. It's that which I'll talk about in this presentation. So industry got together and they decided that the cabling between tidal turbines in an array setting is holding back the industry in its development. So Scottish Enterprise came together with a funding pot with tasks to develop a new cost-effective solution for in-field cable deployment in strong tidal flows. So these aren't the export cables, these are the cables which run between tidal turbines. So Aquatera was lucky enough to be put forward to the second stage of this project, and in a consortium of organizations, we put our heads together to develop a new approach to protect and recover cables in high tidal flow environments, with the aim of de-risking and reducing costs to the industry. So we looked at how we would do that, and we mocked up an array setting here. And we did 3 main experiments. The first looked at how you could potentially deploy a tidal turbine, which may have a jumper cable, and then fall back in the tide, deploying that cable. That's demo A. The second one looked more along the lines of future wetmate connectors, laying the cable across the tidal flow. And demo C, which was the final one, which was an amalgamation of the two. And I'll talk more in detail of that one. So we did this up in Orkney. I don't know those that are familiar with Orkney. In the top right, you'll see Orkney Islands, and if anyone's familiar with Stromness and the Hoy Sound, is the area where we selected to do this demonstration. The main reason to do it in this area was a combination of reasons, from marine licensing to the fact that we were doing this in December, so we'd had limited daylight and we were in close proximity to the port of Stromness. It was also sheltered from very extreme weather, meaning that we could de-risk the marine operations. One of the setbacks was that we weren't exposed to very much waves, but we certainly were still exposed to tide. So the concept all hinged around Green Marine's catamaran gantry barge. This barge already exists in Orkney. It's got very low drag coefficient because of the shape of the hull. It's proven already in the deployment and recovery of tidal turbines in Orkney. So we looked at how we could maybe create a mothership-style vessel which still has the capacity to deploy and recover turbines as well as gravity anchors. But if we put a span deck right across the pontoon, so we're not in contact with the water surface, we don't increase its drag coefficient. But we've then got a multifunctional vessel that can maybe compete with DP. So this is the moored barge that you see in the title of the presentation. So to do this involved significant engineering. We only had a year to do this. It's quite a challenging project. So to design, do analysis, fabricate, test, and get certification from DNVGL all within a year was quite a challenge in itself. This image here is some von Mises stress analysis. You have the sockets on the top and the trunnions on the bottom. The trunnions are located on the end of the deck and locating the sockets on the wetted face of the existing pontoon. So here you can see that installation in action. The decks are modular by design because we wanted to be able to install these with low-tech vessels. That's a Green Marine Damen multi-cap. Each deck weighs 21 tons, quite significant steel. It needed to be safe, and obviously these things cost a lot of money, so it needs to be worthwhile for the future-proofing. So the installation took place in Scrabster, where, as I just said, the trunnions locate into the wetted face of the hull, but the water surface is not contacted, so there's no increase in drag. This is back up in Orkney and Stromness, with the decks now in place and the vessel made ready for cable laying. So in this image, we've turned the gantry barge into a cable laying barge. So in this image, you have a deck tugger, all modular, a powered spooler with the cable. The green thing in the middle is a 5-ton track tensioner, and at the end there, laying inboard, is a multi-angle cable overboarding chute. And you can see we've not compromised the heavy lift capacity of the gantry barge, with the moon pool area still free. So obviously we're not DP, we still need to be able to move around the tidal array. So we looked at an innovative mooring system, and we really expanded out the mooring grid to a 340 by 360 meter area. The buoys are shown in the far corners. We then laid a 15-meter grid on our survey spread so that we could accurately track our position on site. The red line in the middle was one of our demos, which was in line with the tide. The tide's coming up from the bottom to the top of the screen, and the pinker colors across the middle are across the tidal flow, the center position shown. The other thing that we did to try and beat the tide and the effects of the tide on the mooring system is that we put a lot of R&D into sourcing ropes. This rope is a specialist winch rope, which we used instead of wire. It essentially behaves like wire in that it doesn't bury and crush on the drum under multiple layers, but yet it's light and it floats, and the dipping catenary between the barge and the buoy is reduced, so you don't get that increased drag on the moorings, which loads the entire system. You can still winch it in and winch it out like you would wire, but you've got all the benefits of rope. To protect the rope, though, we had to redesign the fair leads. These fair leads were designed for the project. Again, all within a year, from design to analysis to fabrication and testing. These nylon-based fair leads, we call them trumpet fair leads because they look like the end of a trumpet. They allow 360-degree load. They're 20-to-1 D over D, which is the relationship between the diameter of the fair lead and the diameter of the rope. Industry minimum 20-to-1 to protect the synthetic rope. There's low friction, low heat buildup, so essentially they protect the rope. You can load them in all directions. One other thing that we didn't want to do in this moored barge solution was in any way interact with the potential subsea infrastructure that's there, so the tidal turbines could be spinning. We didn't want our mooring lines to be taking an angle from the chain clumps to the barge and interacting with the tidal turbines. So we've got 5-ton subsea buoyancy here. And the idea was to try and create a positive buoyant mooring system at all times. You can see the mooring line there between the buoy and the barge, also not dragging in the sea. This worked quite well. The maximum depth we recorded with depth loggers on these 4 buoys was 3.6 meters. So they did submerge, but not anywhere near to interact with the tidal turbines. One other thing that we did to increase cable stability was to design these simple concrete tire-based systems that we would deploy with the aim to deploy the cable into. Obviously, this would create a need for high cable accuracy. 3 meters is the span between the 2 points. We use this in this system so that when we're laying in the U shape, obviously the cable would follow us if we didn't have it secured in some sort of subsea system. So we pivoted around the corner blocks and then laid into the cable guides before pivoting back around the final corner block, and the 2 clumps would simulate tidal turbines. Some results. This is the results from winching trials. So this is not cable laying, this is just trying to test how far this barge can move on this mooring system with all I've discussed. The blue and the yellow are the actual trials, and the green and the red are just us getting into position. We managed to achieve 123 meters east, and there's a reciprocal, and 103 meters north and reciprocal. So we established that the mooring system was good enough for the needs of inter-array cable laying. The actual cable lay was very accurate. We tracked the cable exit point using an RTK base station on land and a marine surveyor, so we had very accurate position keeping. The green is in line with the tide, and the yellow is across the tide. And we managed to achieve less than 3 meter accuracy, i.e. the cable of a board and chute didn't deviate more than 3 meters over the 150 meter cable lay. So the cable was successful in where we wanted it to go, as you can see in the guide and around the corner block. One report by EMEC suggested that vortex-induced vibration was one of the main causes for concern in the lifespan of the cable. So this potentially addresses that by increasing the stability of the cable. A short video. I have time, so I'll give my voice a rest and let you just watch this 3-minute video. Not sure if it's going to have sound. Yes, it does. Okay, so hopefully that short video puts into perspective the presentation. Last slide, some of the conclusions. So we believe that we've created for tidal industry a multifunctional vessel that's able to deploy and recover tidal turbines, as well as have a modular decking system installed and then be converted to an in-field cable laying vessel. The mooring system that we designed and tested worked well. The winching system exceeded expectation, and we were able to deploy the cable accurately, safely, and effectively. The final slide is some of the consortium companies which helped bring this project together. That's me.
Great, thanks very much, Dan. Now we're going to keep this question and answer bit to the end of the session, so if you can write down, I'm sure, all the questions you've got for Daniel about that project and save them to the end, that would be great. But now I'd like to invite our second speaker, Jim Buston from Jee Ltd, who's going to tell you about the other project under the SE Tidal Array cabling project. Jim's got an extensive experience in the offshore energy industry, having worked in that area for the last 7 years, and manages subsea engineering business development with new clients at Jee. There's a multitude of experience in the offshore area and involved in many large deep water projects around the world. And Jim won the Pipeline Industries Guild Young Professional National Award in 2012, so well qualified to speak in this area, I'm sure. Over to yourself, Jim.
Thanks very much. As you mentioned, Jim Buston, I'm engineering BDM at Jee. I'm standing in for Joe Granston, who was managing this project. So I'll do as good a job as I can, so bear that in mind if you ask me any questions at the end. So I guess a little bit about Jee, first of all. We're a specialist subsea engineering company. Generally speaking, our focus is anywhere from the seabed to the top side. So that middle area there is really where we make our name. We spread across oil and gas and renewables. Generally speaking, we split our business into 5 parts. So we have the design part of the business, we have the integrity management, we have pigging, we have late life and decommissioning, and we have training. In actual fact, we've trained, this is slightly outdated, but we've trained over 6,000 engineers now. That's oil and gas and renewables. So we tend to be known more for our training works. So when it comes to subsea cables, there's a lot of challenges associated with those. And actually, it might be a surprise to hear that around 80% of insurance claims are around failures associated with subsea cables. So innovations in cable protection systems are quite a hot topic. So it's quite common to see J-tubes, for example, at the bottom of something like a monopile. So what that is basically a conduit for the power cable to come down, take the transition, and exit onto the seabed. What you actually get in some cases is where the current washes across, you can get scour, and this has the effect of washing away the seabed, and you can end up then with your cable where it was neatly going onto the seabed becomes leaning down, and actually in some cases where you have mattresses, for example, which might have been put on top of the cables to stabilize them, actually you can have the instance where these mattresses are hanging off the cables where they used to be ground, so they end up putting excess loads on them. So there's a lot of work can be done to improve the design, and we've had a stab at it. On the first idea that we had, it was essentially a J-tube with a straight pipe connected at the base, and then going into a J-tube again where it joins the next member of the array. So quite a simple design, and in practice it should work okay on flat seabeds. The problem comes if you have a slightly dynamic seabed, or maybe the seabed is quite rough. What again might happen is you might start to get spans where there were none to begin with, and spans can lead on to VIV or vortex-induced vibrations, which can cause the cable once again to get damaged and maybe cause the conduit itself to buckle and damage the cable. So our next idea was to, rather than lay the conduit along the seabed, was to have it suspended slightly above the seabed. So have the J-tube end slightly above the seabed and then have the whole span above the seabed. What this meant was you obviously increase the risk of vibration. So we designed in a fairing, which you see on the eye carrier there, which means that as the current goes across, it shouldn't cause any vortex-induced vibrations. This was quite strong horizontally, but what we found in our designs was that actually with self-weight, you could get buckling forming in the vertical axis. So it would be okay if it was fairly stable, but there was a risk there. So as the designs went on, we came on to the third design, which was the triple boom, which we designed to be for the most extreme conditions. So if the seabed was very rough and if you had quite strong currents, the triple boom should work just fine. So the final design incorporated this triple boom system, and you can see the red U-tube, which is essentially a J-tube at either end with a straight conduit in the centre. So either end you have baskets which are in place to hold the ballast. So this would be filled with rocks or chains, and they could be customised to fit various turbines, but we'd try and come up with some sort of universal design for those. The benefits of this kind of modular design should be that the installation process could be much faster, so it could be lowered to position quite quickly. We think this means that by making the ends more of a universal design, it should mean that it could work with a range of different turbine type situations. Also, because it means you have the conduit running the full length of from the array, it means that actually the cable isn't exposed at any point, so it should offer much better cable protection system. And also the beauty of the system is that if it's spanning at any point, there's no problem at all. So what this means is you wouldn't need to do some dedicated detailed surveys before installation. You could go on your basic upfront MBES type results. So into the practice phase of some trials that were performed. Aquatera was the leader at this phase, so Daniel will be able to answer any questions you've got on this part. Essentially, what you see here is performed in Orkney. You've got two cranes which are picking up the structure here. The structure's around about 50 metres, basket to basket, approximately 40 metre span. So in the top left, you'll see a close-up of the basket. What you're actually seeing there, the first thing is you'll notice it's not full of ballast, just a small amount of chain in there. And we decided not to put a great deal of chain in there or rock because the testing was only for a short period of time, so it wouldn't need to have a great deal in there. And secondly, you might notice it's a little bit rusty. There wasn't much point in painting it again because the trial was only going to be for a short period of time. So we've got some quite good footage of this stage of the project, all captured by drone. So I think this gives quite a good overview of the scale. You might recognise the gantry barge there that Daniel showed us in the previous presentation. So in this situation, you have the gantry barge and you have the two multi-cats either side. So the gantry barge in this instance is basically functioning as a spacer between the two multi-cats. So the cranes would pick the structure up, hang it off the side of the quay and lower it into the water, where it would sit just below the water line. This process took a little bit over an hour, maybe up to 2, and then it was ready to be moved. So in this case, we then had a tug to position and drag the units out to the area that we wanted to perform the test. So here, this is Aquatera's mooring system from all 4 corners. Again, it's quite a nice picture there. This was done in a depth of approximately 27 metres. You can see that the water was not choppy at all, very calm. So this was going to be very good for proof of concept, but I guess if we were to do this project again, it might be good to do it in slightly more extreme environment. So here you can see the backside where the structure was hanging from the rear. It's lowered to position where we're then able to start our pull through. So what you actually have is in the U-tube itself, we had a pull-through cable already sitting within the U-tube. So this meant that when we wanted to bring the electrical cable, we could merely connect it up. You can see the picture there from ROV using Chinese fingers, which tighten as you apply more stress. And this meant we could connect and then pull through the U-tube. So through the vertical, down the J, across the horizontal section, around and up to breach the surface. So the key details of note to bear in mind here, the pull-through time in this instance took approximately 4 minutes, and the pull-through loads that were applied to the cable were around about 1.8 tons. Now, again, I think these could be improved if we were to use a cable which had a very smooth outer coating. I understand the cable that we used was just what we had available, so actually there's some area to be improved there. So we've tried to illustrate the benefits of using a protection system such as this. Using the net present value, this compares the U-tube to other more generic methods such as trenching and rock dumping. So what you can see is the U-tube has the very high peak at the start, and the others all have the very low and wide shape at the bottom right there. So what that's actually showing is, for example, if we pick rock dumping, it's showing that actually the cost of rock dumping could be very, very low, but the width of it shows that there's also a large degree of uncertainty with that. So it means that it could equally cost you an awful lot of money over that time. So with the U-tube, the upfront cost is significantly higher than all of the others, but, and I guess this is the crux of the design, it's a very accurate, it's very certain. So we know that actually once it's installed, you're not going to have ongoing costs associated, which you might run into with the other methods. And this might be useful if you're trying to get a final investment decision, for example. So where can we see this being used? What's the future? I think in this space, the future is all around modular design. And being a modular design, this should mean that savings can be made in terms of installation. So the installation could be performed much faster. I think there could be a lot less engineering needed beforehand. We also think that if you had the ends universal, it would mean that it could be used with a variety of different turbines. And hopefully this means that you should save money also on the surveys. So it means that you could go on a very basic upfront MBES type survey rather than doing your much more detailed seabed topography type exercise. That's it from me. Thanks very much.
Thanks, Jim. Thanks for that. Now, we heard obviously from Daniel Wise, the first presentation about the use of a moored barge for tidal cable deployment and operations. Now delighted to invite Anne van Houten from Keynvor MorLift to talk about a project under the Innovate UK SA MESAP programme, which was looking at the use of a DP barge system. Anne's a commercial development manager for Keynvor MorLift and extensive experience in terms of that overall marine operations. Keynvor MorLift's a marine contractor and vessel owner, and I know Anne has had experience directly in the tidal industry with Blue Water, who are involved in the development and deployment of tidal platform technology. So over to yourself, Anne.
Thank you for the introduction and for the opportunity to give an update on our DP barge project. We indeed have some interesting developments over the last period. I'm Anne van Houten of Keynvor MorLift, and I'll be giving this presentation on behalf of a wider consortium. In the presentation, I'll give a brief introduction of the project. I'll cover who's involved, why this consortium has gotten together, and what we intend to do how. After that, I'll take a brief step back and look at the bigger picture and developments in both the marine energy and the marine renewable energy sector over the recent years. This is important because the story of the DP barge, and particularly for KML as a vessel owner, it's important to see the perspective and the wider context in which we would operate and invest into the markets which we wish to aid and serve in the future. This will then lead to an update on the DP Barge project. First, I'll introduce all the partners. IT Power, I'm replacing here for Ned Mintz of IT Power, who is the project lead and project manager in the consortium. IT Power is a specialist renewable energy consultancy with a long track record dating back to the very early days of the marine renewable sector. Then there's KML, who I work for. And KML is the barge owner, will be the eventual barge owner and operator. And we are an integrated marine contractor and vessel owner, operating a fleet of about 10 vessels, from heavy lift crane barges to flat top barges, tugs, workboats, survey boats, and landing craft. We've worked with a number of the leading wave and tidal energy developers over time, from project inception to installation and to decommissioning of some of the other devices. So we have developed a deep understanding of the complexities of what the industry is trying to do. One of the other partners is Rhaegar, who is tasked with developing a bespoke DP system optimized for use on the high energy sites that we aim to be working at. And lastly, there's AMP Falmouth, who will provide docking facilities for the modifications and the conversions that we're planning to do. AMP Falmouth is part of a wider group of AMPs, 3 AMPs in the UK. Now the big question is why we're doing this. First of all, and I'm going to use a slide, actually a graphic from the Carbon Trust, which has been much used by many people over time already. But as the industry is moving forward from single devices to larger arrays, there'll be an increasing pressure on lowering cost and increasing output. And it's in lowering the cost of operation and maintenance and installation where the consortium believe we can help. The next question is, why and how will we be lowering cost? Well, in observing and working in the industry, we made the following observations. And the first is that vessel versatility is key. A developer will ideally only need to mobilize and rely on one vessel to perform a variety of tasks. To name a few, there's the logistical elements at the port of loading, at the port of loadout, where you ideally only would use the vessel's crane and not have to mobilize an additional land-based crane at cost. Then the arrays, of course, also create the opportunity to realize further efficiencies and transport multiple devices or structures to site at once. Once on site, there are various activities such as cable lay, device deployment, subsea drilling and grouting, and more of that. After that, you move to the O&M phase. And in relation to the DP bars, of course, this will mainly be recovery and redeployment, as minor inspections will be done by smaller vessels. And eventually there's decommissioning. The challenge here is how to combine all of these scopes, which will vary from developer to developer, into one affordable vessel. And yes, there are very highly specified vessels out there that can do all of this, and they're often built for very prospering sectors, at least at the time, and I will say more on this later. However, the type of vessels will eventually come at a price tag and a high operating cost and fuel consumption. So readily and affordable workboats won't be able, skip that a bit too early actually, readily available and affordable workboats won't be able to service the full cycle. And this is where we try to aim at the spot in between. And there, as a consortium, we believe we can aid and provide a practical, robust solution. So then, what is the DP barge that we're developing? Well, in summary, the barge will be a generic construction platform to service marine renewable projects from installation through to decommissioning. The DP barge will have the following main features. It will have a bespoke DP and propulsion system, specifically tailored towards working in high energy sites. It will have heavy lift deck craneage to the specifications that the project needs. It will have a large deck space for devices and foundations. It will need to be operable in up to 6 knots tides and 25 knots of wind, and will aim to have a relatively low day rate of 30 to 50,000 pounds per day, which is low compared to highly specified vessels. And I'm giving a relatively fairly wide range here because the DP BART is a flexible concept. It will basically be a flat top BART which we will use as a clean canvas on which only those items the project requires will be painted on. A couple of examples are provided in this slide, but this is of course not an exhaustive list. By only mobilizing the items that the project needs, it reduces cost, but also the risk of cost exposure may the project incur delays. An example of the flexibility would be the solution that we aim to provide for craneage. We'll be able to provide either a modular ringer crane or an A-frame, depending on the project requirements. And such flexibility will be important in industry that is developing and with many players and many different technologies and requirements. Now the next question is, when? I haven't covered where either. Where is an interesting question, and with the UK presently in the lead, but I won't dwell on this. The big question here for us as a supply chain consortium is when. When is the time ready to invest in this and to prepare for this? And this is a difficult question, of course, but to put it in perspective, I'll quickly run through some of the predictions and slides that we've seen in the past from various different people. I need to pre-warn you, this is certainly not meant negative. We are great believers in the industry, and we're gladly seeing and contributing and seeing on a lot of progress, but it's not been as rapidly as predicted. For example, in 2011, some of you might have seen a slide from Renewable UK predicting that 50 megawatts would be installed by 2014. In 2013, the same 50 megawatts would be installed by 2016. Now, 2013 was actually quite a good year generally. There was comparatively successful CFD negotiations, and we also witnessed a high degree of OEM entries and activities in the sector. Nonetheless, we're now 2016, and we don't have our 50 megawatts of installed capacity yet. IT Power did another prediction based on developer predictions and project plans, and it would predict that 50 megawatts would be installed towards the latter end of the decade. Now, these sliding forecasts are of course caused by a number of different factors, and one of them is economics. The marine renewable sector finds itself competing with not only other forms of renewables, but also generally low energy prices. The DP BART will aid to this, but the bigger picture is of course also there. Then we have the marketplace. There's been a high degree of turmoil and volatility in energy markets, particularly in the price of oil. And I will touch on this later to say how it affects the marine energy sector. In addition, the industry depends highly on political support and certainty, and there's of course the technological complexity. Developing an energy device to operate in a very hostile environment is simply not easy. But the main conclusion that we draw as a consortium is that our DP BART needs to be able to absorb these uncertainties and risk, and that a versatile solution is required to be able to operate and serve this industry. And before I give an update on our project, I'll briefly zoom in on the energy markets in general and how this affects the marine environment. The graph here shows that highly specified vessels in 2006, 7, and 8 went out at high rates. This represents a shortage of vessels during a activity of very high activity in the oil and gas sector. As a result of high demand, more vessels were introduced. But at the same time, as we're all very much aware, oil and gas activities dropped as the price of oil dropped significantly. Therefore, there's now an oversupply of vessels in a very depressed market. And many of the operators are operating below their costs and only contributing at rates that partly contributes towards their overhead. The question is, how long is it sustainable? For the sector, it's an opportunity at present, but it's a threat going forward. We cannot really rely, while we can benefit from it now, the sector cannot build on its long-term strategy on the use of these vessels. The prices will inevitably go up again. Therefore, driving the cost down and lowering risk structurally remain of great importance for the sector to succeed. A practical and economical solution for installation, O&M and decommissioning would contribute to this. Now here's our news. We are steaming ahead with our projects. It's because of this that we believe it's still important that risks are reduced. We are converting and modifying one of our recently acquired barges, MorLift 15. He's a flat-top barge of 60 by 20 meters. And we'll be doing this in order to be ready to aid the first wave and tidal arrays. How we manage the risk of sliding forecast and the general industry standard is that the Moraine is a very versatile barge and has many uses to KML as the marine contractor. We will both be able to work in the marine civils industry, but also in marine renewables. It's with this versatility and flexibility that we're able to manage the risks of the unpredictable market conditions. Meanwhile, the modifications for DP conversion and deployment of the barge are underway. Our next steps include a survey of the barge at AMP, and during this survey we will determine the extent of work involved, and we'll confirm all of this in further detail. Then we'll install the removable propulsion units, and the DP controller development is ongoing. I'll also give a quick update on this. Raygar has developed the DP control system for use in smaller commercial workboats to make it more affordable and cost-effective. It's designed specifically for the use in strong tides. It has a joystick, auto position, weather vane, and ROV follow modes. We've recently tested the control system on our surface vessel 7C. The test included operation in up to 8 knots of simulated tide and rough conditions, and were successful. Overall, the trials proved very effective and alleviate demands on the master, and we are very confident that we can apply a similar scheme onto our Moraine. In conclusion, the consortium is proceeding with our DP barge project and believe it can add value to this next stage that the sector is entering. And we're doing this despite the risks and the challenges of the current market by providing a versatile, practical, and very economical solution that is aimed to reducing the overall cost and project risk. And we look forward to servicing the first arrays with this barge. That was it. Thank you.
Thanks, Anne. Okay, well, sticking with the vessel theme, you've probably spotted through this particular session now. I'm delighted to introduce Commodore Steve Jermy from Mojo Maritime, who's a chartered marine renewable energy technologist. Steve's got a very interesting background in that he joined the Royal Navy after his first degree and had a very successful career involving commanding 4 warships, a destroyer squadron, and his final appointment as Commodore Fleet Air Arm. I guess many of us would be able to put that in our CV. 2010 he moved into the offshore renewables area, and with Mojo he specialises in offshore array design, marine operations for installation, operations and maintenance. He also leads Mojo's marine renewable policy engagements. So Steve's going to tell us about another MESAT project looking at the concept and development of the high flow 4 vessel.
Thank you, Neil. When you take over command of a British warship, one of the first things you do is stand up in front of the ship's company and do what's called clear lower deck. What you do at that is basically tell them how it's going to be for the 18 months in command, and in return they get a chance to look at you. There's a very good story of a colleague who was taking over a ship which was a not happy ship, and he stood up in a very collegiate way and he said to them, I want you to think of this ship not as my ship, not as your ship, but our ship. And somebody from the back of the audience said, oh good, let's sell it. I'd like to think that when I finish this presentation, you'll perhaps want to buy this ship that we're talking about. I honestly, truly think it's a game-changing technology for tidal energy, and I hope that will become clear, not least of all because we've got the mathematics to prove it. This is the structure of the presentation. I'm going to talk about what we see as the tidal energy challenge in Mojo, a bit about the ship in technical terms, a bit about the ship in operational terms, and then the economic impact of the ship on the sector. I should say that we in Mojo are specialist offshore engineers and marine operators, and we do both. Our most recent projects were in the summer to put the cables in for Magen, and then in the autumn put the Delta stream in for Tidal Energy Ltd in Wales. And we've been pretty much in and amongst Tidal Energy for the last 10 years. So, what is the Tidal Energy Challenge? Gravity bases, we think, probably have a role, but we're not sure if it's a long-term commercial role at scale. They are expensive and they're difficult to install, and they tend to rely on the assumption that the seablade is flat, which it isn't. We're not sure about jack-up barges either. We've had bad experiences with them. We don't use them now. Vortex-induced vibration is an issue for them. And so we believe that actually the answer is this. It's a dynamically positioned vessel, not dissimilar to the one that we've just heard described, but using monopile devices which are drilled into the seafloor. That's our experience which tells us that, and we're very happy to be questioned on it. But I'll be working on that assumption in this presentation. What's the issue? The issue is that we're working at 10 knots, tidal streams at springs, and it's akin, as my technical director says, to trying to put up wind turbine farms in a hurricane which blows 6 hours one way, gives you an hour, and then 6 hours the other way. Pentland Firth is the area that we're looking at, and on this slide, you can actually see on the top, you can look at the tidal streams. It's 5 meters per second up there, at the top of the tidal stream there, and what I would just point out is the maximum DP capability of most ships is around about 2.5. That's even the most modern ships. You can see wave height is also an issue, and last but not least, wind speed. What does that give you? It gives you this problem, which is you can only operate with a current DP2 or DP3 ship in those windows. You can also see on the right-hand side just how sensitive the whole operation is to weather. So that really is a problem. Vessel utilization down about 10 to 15%, and an operation which is very sensitive to risk. Probably okay for early stage devices, but there's no way that we're going to be able to work in a commercial sense, getting large numbers of turbine at sea in this situation. So this, we think, is the answer. If we can do that, which is push the DP capability up to that sort of capacity, then we get that. And I think in such a simple slide, which is produced by my naval architecture colleague, Simon Hindley, you will really see what is this fundamental part of this ship. So what are the technical parts of the ship? We're looking for the Holy Trinity, which is a dynamically positioned capability of 10 knots. Enough deck space to do what we want in the ship, and last but not least, enough craneage as well. And we've designed the ship with a 250-ton AHC offshore crane, and we don't think there'll be much tidal technology larger than that. And certainly the largest turbine that we can imagine is going to be 230 to 250 tons. We'd like the ship to be able to do everything: foundations, turbines, cables, and last but not least, operations and maintenance. And our commercial targets were to build the ship for a price of 35 million, and to have a charter day rate of around about 35K long term. That's a long-term charter, not a short charter. And that's what she looks like. I'll say a bit more about her in a video, because I've got a video coming up which sort of really gives you a sense of the whole operation as it is. What's her DP capability like? This is using the standard IMCA simulation. GE did the DP capability analysis for us. And the way that we designed the model for GP to develop was we gave them 45 degrees HS3, that's 3 meters swell on the bow, just short of 10 knots on the bow, or into 10 knots, and 50 meter wind on the beam. What that then gave us was a model, and this model, if it works, let's see if we can get this working. Don't know, I've got the IT guy up there, if we can just activate the model. Don't know if I'm going to be able to get this working. Here we go. Right, this is a GP model, and it's a simulation. What I'm going to do, or what you'll see happening is that around about, in about 20 seconds or 15 seconds, there'll be a thruster failure. The vessel's got 4 thrusters. The thruster will fail. There it goes. And so at 10 knots in a tidal stream, she loses a complete thruster without knowing the thruster, and yet manages to hold station. That's important for us because it's critical to risk reduction. So in terms of a long-term operation, we see this as a really critical part of it. We actually produced those conditions and put them on it because we thought we'd break her. We didn't break her, so actually we really can't find what are her proper limits, but certainly we can't imagine wanting to operate in much more than 50 knots of wind. We've tank tested her in Vienna, and that all looks good. Tank tested at a 1/13th scale and 1/26th scale, essentially to confirm all our mathematical modelling, and so we've done. So that all looks good. She's probably a little bit lumpy on the bows. We might have to find those off in a bit, but otherwise she works and she will work. What does it mean operationally? Again, this is another video. Let's see if this will work. No, not quite. I can just have the IT support for this video. There we go. I'm just going to let you watch this, because really what you're seeing really here is a tidal systems approach. It's a systems approach to tidal engineering, and I can't help but feel it's the key to getting this operation working. You're seeing cut-in animations of the ship, but also existing technologies which we're using and have built the ship around. That's the bow drill, or the template for the bow drill for the monopile. Again, this exists. It was a cooperation between Bauer and ourselves. We went from the drawing board to having this in the water in 6 months. A job for Voith to put their turbine in. Self-leveling, so we can get over the problems of the unflat seabed. And this is the real template, and then again you can see splitting to the analysis. Vessel doesn't have a moon pool as such, but there is a hole in the deck which allows us to operate from 2 areas of the ship. The critical issue is that actually we need to be able to drill through the tidal cycle. Bow drill operates at around about 1 meter to half a meter a second. Sorry, half a meter, that would be fantastic. 1 meter to half a meter an hour, so that actually for a 26-meter monopile, which has got 11 meters below the sea floor, that's between 11 and 22 hours drilling. So you can see how important it is that actually we drill through that tidal cycle and work through that tidal cycle. Again, these are cut-ins from real operations done from North Sea Giant. Again, the vessel built entirely around these ideas, so optimized for tidal energy. That's the bow monopile you're seeing there. Again, as I say, 26 meters, 15 meters above the sea surface, sorry, above the sea floor. The reality is that almost all of the operations which are not drilling like this will probably be done in slack water periods. But the fact is that we can do these time-consuming operations, and I'll show you how time-consuming foundations are shortly. We can do these time-consuming operations throughout the tidal cycle. The drill going in, or the monopile going in the grout. The critical issue in this vessel is to be able to do everything. So as you see, she'll be able to run the drilling, insert the monopiles, do the cabling. I do think cabling, I was very interested to hear the presentation on cabling. I do think cabling is one of the Cinderella areas of tidal. Again, this is the real monopile which was put in for the Voith turbine. We've got 3 or 4 suppliers for the A-frame, different ideas. We're still not sure exactly what this will be like. Then actually you come to the logistics idea. The critical issue is to be able to get the A-frame to allow us to actually load on turbines and anything that we need from the port without assistance from additional craneage. So essentially we can work from austere ports. As a former ship's captain, she'll be a dream to handle. So to be able to operate into these places is fine. She draws about just under 6 meters. But in terms of ship handling, I can't think of anything, anything that's easier or more capable of handling. Voith turbine's about 230 tons at the moment, actually. And for oceanographic reasons, we can't envisage there being much bigger than that. Again, happy to take questions on this. This is the real Voith turbine going on. Again, using a lifting spring which we made. And again, I think the critical issue you see here, the arrays will not be like this. They'll be in rows, I'm certain of that. But what's important is the seafloor isn't flat. And so that's, again, why I listened with interest to the cabling discussion just now. There is the vessel. The Voigtschneiders are critical to performance. We think they're much better, and I can again take questions on that, much better than azimuth thrusters. And we have a terrific deal with Voith, who have been very supportive of us. We have an exclusivity deal with them, which is almost more useful than the patent. There are the A-frames, 2 knuckle boom cranes as well. She's not the prettiest of ships, I should say, but like all functional ships built for a purpose. There's my managing director, ship handling using the Voith simulation facility. I think there'll be a bit of a race between which of us would like to get our hands on this first. He'll probably win, but I would love to. And last but not least is cabling, designed and built with cabling in mind. And you can see this for offshore wind, and we do think there's a market for the ship in offshore wind. The dynamic position system is so powerful that not only can she take 5 meters a second, that's 10 knots on the bow, she can actually dynamically position at 5 knots sideways, so 2.5 meters per second sideways. So it makes her an incredibly flexible cabling vessel. Okay, I think that gives you a really good, I hope, a really good understanding of how we plan to use her. Here she is with a Voith turbine. Smaller turbines, the Tacados, just for illustration, again set up for cabling. So what does this mean? Why? We have in Mojo a systems analysis, a marine operations analysis software called Mermaid. We use it for our own planning, internal planning, and a number of other areas. What you're seeing on the top screen there is a task analysis which we've used to actually have a look at it. But not only do we do it for our own planning, we, for example, planned the TEL operation and the cable installation. We use it for R&D as well. Essentially what it does, it allows us to simulate an operation against a lot of hindcast data. So what we've done for this particular ship is to simulate her against a conventional vessel in both medium energy and high energy sites, assuming monopile foundations in the bow drill. And the results are fascinating. This is a busy slide. I don't want you to worry about it other than to say that the critical area, if I can get this to work, is the time. So this is a medium energy site. It's Skerries. And if she's in the site, she'll do the job in just about 250 days, putting a 30 megawatt installation in, versus a conventional ship, which is 589 days. That's a medium energy site. I should say that if it's a high energy site, the improvement in performance goes up geometrically. What does that mean? Here we put a 100 megawatt medium energy site, and you can start to see the improvement. On the left-hand slide, you're seeing the overall improvement in installation time. And so you can imagine that actually with those sort of charter rates, you can imagine how much the costs are coming down. But the real win, it's not easy to spot initially, but the real win is here, this early yield. So by getting the turbines in the water early, you're starting to produce a significant amount of early yield. And on this particular site, using the current strike prices, the net benefit of the ship for a 100 megawatt installation is just short of £250 million. £250 million. Again, all about early yield, and those improvements are geometrically higher, or likely geometrically higher, in a high energy site. What's the impact on levelized cost of energy? It's here. That's offshore wind round 3, and we think that we're going to be around about here. 116 megawatts, 116 pounds a megawatt hour is what we think we can get Tidal down to. What's interesting is that that figure is insensitive, or relatively insensitive now, because of the improvement in the vessel to charter rates. So whether it's 35, I think if we move the charter rate from 35,000 to 55,000, it moves it from about 116 pounds a megawatt hour to 120 pounds a megawatt hour. You get to the stage where it's really the capital expenditure is what matters. We're not stopping here. We see this again as part of a systems approach. She is the heart of a systems approach to tidal energy. But we're not stopping here. About 15 months ago, we won a project with IKM, which is a Horizon 2020 project, to actually design a high-speed ROV. Current ROVs tend to operate at up to about 1 meter per second, 1.5 meters per second, but we find that they top out after that in high-energy tidal sites. And we're hoping to be able to design an ROV which will get us up to at least 2.5 meters per second. We're not sure at the moment what improvement that will give us, but what we're trying to do all the time is chip away at this critical path, the critical path to actually reducing levelized cost of energy. Bow, meanwhile, are looking at the drill as well, and thinking through what will be the implications of larger turbines, 1.5 megawatts as opposed to 1. And again, there will be other things for us to work on in the future. So, I think that concludes the presentation. I mean, if I were to summarize, I think this is a truly game-changing technology for tidal energy. We have the maths and the analysis also to prove that. We're in the middle now. We were slowed down in actually getting the ship bought and built, but we're in the middle now of an investment raising period. We were acquired last year by James Fisher's, and that took us a little bit of time just to get our ways through that. But we're now working with James Fisher, with GE, who are providing content, with Bow, who do the drill, and with Voith, who provide the propellers, to actually get this ship funded and built. And I'm conscious that with a Scottish executive person in the audience, that we'd love to build her in this country, including in Scotland, if you're interested. So, I'd like you to think of this ship not as my ship, not as your ship, but as our ship. And if there's a call of let's buy it, that would be great, because we're ready to get this ship built. Thank you, Neil.
Great, thanks very much, Steve. Okay, so we've had a good contrast in particular concepts and ideas around about vessels for Tidal. But now I'd like to just kind of switch topic a bit. And our last speaker today is Simon Cheeseman, who's a wave and tidal energy specialist with the Offshore Renewable Energy Catapult. And Simon's going to tell us a bit about a couple of initiatives that Catapult have been working through over the last year or so. Now, Simon's a very experienced marine engineer, having both worked in the commercial and public sectors, and joined the Catapult in February 2014. Simon's responsible for managing the Catapult's marine strategy and identifying the wave and tidal technology innovation priorities for the Catapult, and also managing the Catapult's regional engagement programme. Simon, before the Catapult, was with the Energy Technology Institute, where again he was leading on their marine programme. So over to you, Simon.
Thank you very much, Neil. I'd hardly recognise myself there, but live up to those expectations. Good afternoon, everyone. Thank you very much for your stamina in staying on. So the good news is this is the last presentation of this session. The bad news is that it's about turbine reliability. I haven't got any embedded videos. I haven't got any Gucci real-life pictures. A few artist impressions, perhaps. So I think it'd be appropriate to lock the doors now. Don't let anyone else out, and let's rock and roll. Okay, what I'm actually going to tell you about is our tidal power takeoff reliability simulation project, TIPTORS. It is about tidal turbine reliability, but it is very applicable to the session. Before I tell you about that, I'll do a little bit of PR on the Catapult. So we're a government-funded research organisation. That's nothing to be frightened of. We've got 120 people spread across 3 sites. We provide a range of services, both bespoke and collaborative, where our main role is to draw industry and academia together to look at technology innovation to make wave and tidal and offshore wind competitive and be part of a future energy mix. As Neil pointed out, my role is wave and tidal sector specialist. I also run the Catapult's regional engagement program that puts me out in the regions to knock on SMEs' doors rather than them having to travel all the way up to Glasgow or to Blythe or to Levermouth. Okay, so tidal turbine reliability. Some excellent presentations have preceded me, which are all doing valiant work, looking individually at sort of subsea architecture and methods to carry out installation. But surely that will all be in vain if the tidal turbines that are there to generate power suddenly fall over because of unplanned component issues. And so what we've seen, and we've seen it in offshore wind. If you've got any knowledge of offshore wind, you'll see that it's still dogged by quite considerable reliability issues. For offshore wind, it's slightly easier to get an engineer out to a turbine. Helicopters are already on standby to drop these people off onto the turbine. flick the switch, replace a component if that's all it takes. But obviously, you know, and it's obvious that for Tidal, and as Steve Jermy sort of pointed out, you know, the issues around having to wait for a slack period time to do either an installation job or a retrieval job are quite enormous. And so for Tidal, you know, the thought of numerous unplanned maintenance events for Tidal is quite horrific and could significantly affect the cost of energy. For first arrays, that's not the sort of message that we want to be getting out there. We want to talk about products that are actually highly reliable, that do the job, that can be installed and operate under the water successfully for those planned periods before the next sort of scheduled maintenance. So the sort of things we see, and I may or may not use this without taking out some people's vision, is around here. So where you've got some sort of pitch control system for turbine blades, underwater you're going to get a lot of turbulence down these blades. That's going to manifest itself into the nose cone here, through the bearings and into the gearbox. No different from offshore wind turbines where you get that same air loading turbulence manifesting as vibrations down here. What we're commonly seeing is failings around pitch control systems, failings around bearings, manifesting themselves as failings in gearboxes, and our old friend power electronics at the back end is where we're seeing a lot of problems. So in terms of looking at how we could sort of cope with that and deal with that, what the Catapult decided to do was sort of commission a project that actually looked specifically at tidal turbine reliability issues. There are a lot of lessons to learn from wind, even though it's still experiencing reliability issues. The problem we've got in tidal, though, is that we've actually got no credible historic data to use to design our systems at the moment or to gauge performance. So the objectives of this project were really to come up with some sort of tool to help that sort of design process, provide designers with a simulation tool so you can sort of plug and play components, so you can actually look at where the pinch points are in terms of your design, and then produce a database of components to feed into that simulator and actually look at where components are starting to fail, looking at their failure modes and that sort of thing. And so reliability still remains a major issue and is actually very critical for ensuring first arrays actually raise confidence for the technology. So the idea of this project was to certainly try and instill confidence in the sector. So the broader program then was actually in 3 phases, and it would draw best practice from other sectors in terms of designing this sort of methodology. So all large sectors, you know, automotive, aerospace, defense, all have methodologies for going through their design processes. And so, you know, tidal energy would be just the same and needs its own way of looking at design issues. We'd also look at the failure modes in wind and translate those into tidal. And we'd also make an assessment of the unique operating characteristics of tidal turbines and understand, most importantly, the physics of failure. You know, what's likely to cause the failures? What have we seen so far in the relatively short life of tidal devices under the water? And as a result of that work, we'd then develop a specification for our reliability prediction tool and go on to collect real performance and real component failure data to inform the whole project. So phase 1's complete, and so this is my sort of reporting on the outputs of this. There is a report on our Catapult website of the findings from the work that we've done so far. That's a free to download report. So the first phase was conducted over about 6 months. Collaborative project between ourselves, Ricardo and DNV-GL. We also had support from academia, from Durham and Sheffield universities, and also from the predominant sort of tidal developers at the time. And what we did was we took a systems analysis approach to develop these process models, and working closely with Ricardo, whose background is sort of in automotive, and DNV, who've done a lot of work across standardization. And we used these and adapted these for the tidal sector. So that methodology now sits there ready to be validated. The specification for the simulation tool sits there ready to be built. And the construction of the component database is there ready for us to go ahead and build. So the second phase, which will be in the future now, where we're looking at consortium, we're looking at sort of funding opportunities to take this forward. This will go ahead and actually prove that methodology and validate it. And the important thing is to actually collect real data. So, we've heard a lot about tidal installations going forward. There's a lot of good work about putting stuff in the water. We need to actually collect performance data now and learn from that. The time is not to be competitive at the moment. The time is to share learning and share lessons. And so a collaborative approach is what we need at the moment. Also, spinning out of the next phase, we hope to develop a smarter condition monitoring system and also look at embedded sensor technology. What we've seen so far is a lot of damage to systems actually occur before they're even installed. So if you imagine your tidal turbine being shipped along the road, going to a port, being loaded onto a vessel, or even towed out to sea, a lot of that bearing damage is actually incurred before the device is actually installed, just simply by bearings that are designed to rotate, just sitting and flattening common surfaces. So we need a different type of methodology in terms of transportation. We need a different way of thinking about how we study the effects of damage to components. So typically, we've looked at sort of debris components in oil. By the time you get to the point where you've got debris in oil, the damage is already done, and you're already on the countdown to a failure. What you need to know is when will that failure occur, and do I, turn up the wick and really push this device so that I get the most out of it, or do I pull back, throttle back, and let it coast to the next planned maintenance event? And that's the sort of sensor technology we need, which is sort of easy to get your head around if it's a single device in an array. If it's a large array, though, of 200 devices, then that's a lot of data to crunch. And that's where we get into some smart data management. And so we need to do some work around digitization of systems and understanding how to manage all that information. If you talk to a lot of offshore wind engineers, they're saying we've actually got too much data. We don't really understand what's going on. We need to be able to simplify this and make it more intuitive so that when the alarm bells ring, we know exactly how to react. And that'll be one of the things that we'll look at in the second phase of the project. A lot of the work we do in terms of looking at reliability of systems we're able to do on our drivetrain test rig, Nautilus. This is based at our facility in Blythe. And there we're able to do work with tidal developers, not only to understand their existing systems, but help them in sort of future design phases. We're able to carry out accelerated life testing on turbines, and we're able to do work around developing condition monitoring systems and looking at sensor technology. In addition to this, we'd gather data from systems that are on deployment at sites like EMEC, and also look at work that we get from sort of academia in terms of looking at other offshore wind installations. The final stage of the project, phase 3, will really be the commercialization phase. So what we're aiming to do here is put out tools for the industry to use that will enhance the design process and make it easier to produce second, third generation turbine technology. And also look at sort of embedded sensor technology around embedded sensors in blades and along the drivetrain itself. Part of the phase 3 will then be issuing lessons learned to industry and also a sort of roadshow of conferences such as this. I think in conclusion, I think the main purpose of this project, has been increasing confidence in the sector. And I think we've got a good handle on what the issues are now and what we need to do to resolve these. In terms of being able to develop sector-specific processes and tools, it's all perfectly viable and we can do that. In understanding the physics of failure and making learning available to the sector, we're starting to do that. As I say, we've got a report out there on our website now which I'd commend to you to look at and come back to us on. And it also helps to help the UK to remain at the forefront of tidal energy technology development. So I'd like to thank those that have been involved in certainly the first phase of the project, which has been Ricardo, DMV, the advice and support from Durham, Sheffield universities, support from EMEC and tidal developers, including GE, Andretz and Atlantis. If you've got any questions about forthcoming phases, you're interested in being involved in the second phase of the TIPTORS programme, looking at tidal turbine reliability, sensor development, do come and have a chat with me. And as I say, our report is available on the web.
Great, many thanks, Simon.
Okay, thank you very much indeed.
And thanks to all our speakers for very timely presentations. Everybody's stuck to the task magnificently, so thanks very much for that. Now we're going to move into question and answer phase now, but we're also expecting Bailey Nina Baker to join us from Glasgow City Council at the end of the session, around about 5:30, to really give a welcome address to Glasgow and for the civic reception which will be held at the Science Centre across the road from the SECC. So I appreciate it if you can remain seated at the end of the session, end of the question and answer session, and Bailey Nina Baker will give a very short 2 or 3 minute address at that point. But anyway, let's go over to the questions. I'm sure there's plenty there. We've had 3 vessel projects which I guess you could compare and contrast there, and some really interesting developments with the Catapult and in terms of other cable protection systems that Jee talked about. So over to you. We've got roving mics there for anybody who's got a question just now. Thanks. Could I take the gentleman just in the back there first? Yeah.
Tim Probert from Renews. Question for Simon. It's just on the phase 2. Have you got anyone signed up for that already?
Sorry, have we got people signed up?
Have you got any developers signed up?
Yes, we have, yeah. So the developers that supported us in the first round are on standby to carry on. One of the things we did for offshore wind is we had what we called our Sparta project, which was taking offshore wind performance data and anonymizing that and sharing that across the contributors for a sort of peer review process. That's a sort of collaborative approach we'd like to see certainly for wave and tidal going forward. And obviously at the moment, you know, it's early days for tidal. There's a lot of sensitivity about performance and certainly about IP. But I think the message here is to make the sector commercially viable. You know, it's about collaboration at this stage. And so, you know, there's a lot of support from all the tidal turbine developers actually to support, you know, a reliability program. It's not the sort of thing necessarily they've got enough time or funding to actually look at it in enough detail themselves. So again, a collaborative approach actually helps to, you know, make that happen.
Did you say who the developers were?
Did I say who they were? Yeah, so the ones who have helped us up until now and who are on sort of standby, the likes of GE, the likes of Atlantis, the likes of Andretz. We're also in sort of conversation with Tidal Energy Limited.
Okay, and when will phase 2 start?
Sorry, say again?
When will phase 2 start in earnest?
I'd imagine we'd like to kick that off probably later on this year. But in terms of the planning, that's actually happening at the moment.
So Atlantis' first phase 1A, could that feed into your phase 2 of your Catapult project?
That's what we'd like to achieve, yeah. Yeah, so anything that's in the water at the moment, certainly devices going to EMEC, we'd like to be able to, you know, get access to that sort of performance data.
Okay, thanks. Okay.
Thank you.
Okay. Next question, so there's a gentleman just in front there as well. Thank you.
Simon Chapman from Atlantis. Question for Jee. Really interested to see your concept there. Just wondering, how does that work with dry mates, wet mates, and what are your thinkings in terms of the actual connectors as well there?
Well, we're having some discussions at the moment with wet mates, so it needs a little bit more engineering at this point, but engineering is underway. So yeah, it's an ongoing thing.
Okay.
So I don't exactly answer your question, sorry.
Okay, fair enough. Thank you.
Okay, another question? Yeah, gentleman over here.
Hi, Keith Anderson from Wood Group. I was interested to hear a couple of the earlier presentations about some concerns with VIV, obviously a valid mechanism, but do we have any operational experience of it leading to challenges and degradation of cables in situ?
I'll go for this. The only cables that have really been exposed to this sort of environment, the best ones to look at would be the EMEC cables. So EMEC have commissioned a study annually via ROV and also Diver. I myself was one of those divers that did that survey over the years for the early days of the cables. So they do have a record visually of the degradation created from the wave site and the tidal site. And they have a report out in the public domain which you can get hold of, but there's been no actual detailed, they're not taking a cable out and put it through any structural analysis or anything like that. So it's really the EMEC report is probably the best source of information at the moment. But obviously, the other way to look at that is there's plenty of disused cables which have spanned islands of SSE. There's lots of cables out there. They tend to just, once they reach their end of life, stay there. But they're a wealth of information as well.
Okay, no, thank you. That's maybe some of my thoughts. It's just, as a concern, I guess, it had been raised, and we're looking at almost analogous to a bridge link between structures as part of a mitigation against something that, how big a challenge is it, I guess, was my comment, and you sort of answered part of that, I think. Thank you.
Okay, thank you. Okay, another question, lady here.
Hi, it's Rebecca Sykes from Lloyd's Register. My question's for Simon. Just picking up on that point that you made about the reliability and some of the damage that's occurred actually during transportation. Is that going to be a part of the project that you're working on in terms of reliability? Because most people do tend to just focus on the operational phase of the use of the device, but not necessarily all the damage that actually is accrued during transportation with different suppliers of components, different supply chains. There's actually going to be quite a lot of disparity, I would imagine.
Yeah, thanks for the question, Rebecca. I suppose the short answer is yes, and a lot of that learning comes from other sectors, interestingly enough. And that's the sort of lessons learned piece that we can draw across into Tidal. I think that the focus of the project is definitely, the physics of failure. Where did the failure manifest itself? Was it when the thing was first switched on, or was it, downstream when it was being manufactured, and maybe there was a process in the manufacturing that actually initiated the failure. So yes, collectively, we collect all that sort of learning and data together to try and put it out there for people to understand, how better to support and transport and own and manage these systems.
Thank you. More questions? Yes, sorry, Bill in the front.
Yes, I'm Bill Mowat from Gills Harbour in the Pentland Pasture. Yes, I saw the High-Flow 4. I saw Richard Parkinson, Captain Parkinson, showed us his initial thoughts on this and his sketches on his laptop. Must be 2 or 3 years ago now, and I was very impressed with the concept then. But obviously work, as Jeremy told us, has been continuing. But does the panel in general think there could be an element of a chicken and egg situation here? And there could even be a situation whereby offshore wind is pitched against tidal stream when it comes to the contract for difference after 2018. What I was kind of concerned about was, yes, I thought to myself that Tidal could probably make it if they could do what Tim Cornelius was talking about earlier on today, proceeding with the stage 1C, is that right? Yes, 1C of the Inner Sound project. That would sound feasible. But anyway, is there a conflict with the CFD rules, and does that mean that there could be a Tidal pitched against offshore wind? And anyway, that's the general question.
Shall I start?
Please, Steve.
I think that there is unlikely to be a conflict between offshore wind and tidal energy. They're very different sources. I think what is sad is that people don't see the power density that's available in high energy tidal sites, which is orders of magnitude higher than offshore wind, and some of the other advantages, but I think we just have to sort of live with that. I think that there is a issue which is a philosophical issue in this country, which is the general approach seems to be that we will provide high strike prices, so £305 a megawatt hour, to draw people through the valley of death to commercialization. And I watch across the Atlantic with the French providing about 150 million euros upfront capital support. And I'm not sure if we've got this bit right. They've got a lower strike price, and we, I think, need, this is a NASA type approach that I think is needed. So I'm not sure that's right. In terms of chicken egg, yes, there is, and it's because of that. And the problem is, I think actually that, Atlantis are in the audience, they've got to raise a significant amount of capital. You know, my working figure is that every 500 megawatt wind farm needs £1.5 billion worth of capital. So to me, assuming that it's something similar for tidal, that's for a 100 megawatt installation is about 300 million. These are very, very large amounts of capital. With the sort of technology that I was talking to you about there, we can massively improve, reduce the risks and improve the yield. But we sort of need the projects underway. In a similar way, Atlantis and others have said to us that they'd like to have the ship in build because they can then go to financiers and again produce a much more improved financial case. So yes, there is a chicken and egg problem actually. We will work our way through it. It would just be really neat to be able to do it with a little bit of more government support. I've talked to BIS about support to the ship, and I'm afraid that the response was that actually we do not support shipbuilding, notwithstanding that we presented this as a part of the UK energy supply chain. I'm hoping that we will over time actually manage to change that mindset, but at the moment there is a chicken and egg problem. It's one that we're having to work our way through.
Thanks for that, Steve. Okay, I think I'll draw proceedings to a close at this point. So maybe we could just thank our 5 speakers for the excellent presentations this afternoon.